Here's a summary of the problems you should know for VCE Algorithmics. It includes the main ones on the study design, plus a few other useful classic. However, it's great to see as many other problems as you can. The travelling salesman problem asks, is it possible to visit every town or a node in a graph exactly once, returning to the start? That's the decision version of the problem, which is NP complete. The optimization version asks what the lowest possible cost is, which is NP hard. See my video on complexity classes for more on this. They can both be solved by brute force in big O factorial time, since we need to potentially try every combination of vertices. Backtracking allows us to stop when a solution is already higher than the minimum. Hill climbing and simulated annealing work here by generating a random solution and then trying to improve it, more likely to work on a complete graph for the optimization problem. The greedy design pattern tells us to visit the nearest next unvisited vertex. It's quick, but probably suboptimal. If you get something in an exam that could be solved like the travelling salesman problem, it will probably look a lot like the travelling salesman problem, moving around a graph in the shortest possible time. The graph coloring problem also has a decision and optimization problem. It asks us to color every vertex in a graph so that no two adjacent vertices share the same color. Like the travelling salesman problem, the decision problem, can it be done with M colors, is NP complete, and the optimization problem is NP hard. Like travelling salesman problem, brute force works by trying every combination of colorings, which is exponential v to the power of m for v vertices and m colors. Backtracking stops as soon as a clash exists or we use more colors than a previous solution. Hill climbing and simulated annealing work by making a random coloring, counting the clashes, and then tweaking something to try to reduce the number of clashes. There's no guarantee it will find a solution, so it's good if we're trying to minimize the clashes in a real-life context, but we can accept some clashes. To use the greedy design pattern, color each vertex with the first color not shared by any adjacent vertex. Again, we're not guaranteed to find a solution. In an exam, graph coloring can be used to model clashes. For example, assigning kids to classes where certain pairs of kids can't be in the same class. Make sure you specify what nodes, edges, and colors represent. You may have heard that all maps can be colored using a maximum of 4 colors. This is only true for planar maps, i.e. a graph with no overlapping edges. For more complicated graphs, you may need more colors. The 0-1 knapsack problem has a different feel. We are choosing from a list of items, each with a particular weight and value, and each one can be included once. We have a knapsack with a particular capacity, and our aim is to maximize the value without going over the weight limit. It's NP complete. Again, it can be solved by brute force. Each item can either be included or not, so for n items, this is exponential, 2 to the power of n. For backtracking, we can stop when a solution goes over the limit or is worse than our current best solution. For hill climbing and simulated annealing, we can make a random selection of items and swap them in and out to maximize the value while staying under the limit. A greedy design pattern would have us find the value to weight ratios and then choose the items with the highest ratio until our bag can't fit anymore. Of course, we really learn the knapsack problem as an example of dynamic programming. We build the solution up with one item and then with weights from 0 to the maximum capacity. Then we add another item and work up the weights and so on. This gives a solution in big O of n times w time, which seems great, but it's actually pseudo-polynomial, so the problem is still NP complete. In an exam, you'll recognize the knapsack problem when costs and weights are mentioned, but there is no graph. Careful not to confuse it with the multi-item variant, where we can take many of the same item. These are the main problems. I'd also consider reading up on the coin change problem, a simpler example of dynamic programming where we aim to provide a quantity of money using the smallest number of coins available given particular denominations. The n queens problem, placing n queens on an n by n chessboard so that none are attacking each other. The halting problem shows the hard limits of computing. The subset sum, we aim to see if a subset of numbers in a particular set can be found to sum to a particular target. Lots of problems are reducible to this. Of course, you also learn about minimum spanning trees, transitive closure, single source shortest path, and sorting algorithms. Leave questions in the comments and like and subscribe to see more videos.